Okay. Now, very one of the important things about that will be very important for the reactivity of the alkyl halogens is that bond strength. Okay. So suppose if you have carbon fluorine bond and different halogen bonds, carbon chlorine and then carbon bromine and carbon that iodine bond. So in terms of kilocalorie per mole, this bond strength is almost 110, and carbon chlorine comes at 84, and carbon bromine is 70, and carbon iodine is 57. So with C this one, so you can say in the periodic table down the group that a strength decreases very significantly. You see this bond strength. So here it is easy to remember because increasing the bond length. Okay, bond length will increase. So if we talk about the bond length, so you need not to memorize this data, but you should know the rules that will bond length will increase and bond strength will decrease, and it's a reverse. So fluorine, carbon fluorine bond is very strong, 110 kilocalories. So once the carbon fluorine bond forms, it will not react with almost it will not react with anything else. So similarly, carbon iodine bond is very fragile. Okay, so almost half than the fluorine, so it's very reactive and the compounds are not that stable. Okay, so next is the synthesis. So let's talk how do we make a carbon halogen compound. So carbon halogen compounds, as we have seen in chapter 3, that first if you take suppose if you have a carbon halogen compound, this methane, okay, and you take halogens, mostly chlorine, this case. So chlorine, and you take light, okay. So in the presence of light energy, so this if you take excess chlorine, then all the hydrogens will be replaced via a free radical mechanism. Okay, so this is the free radical mechanism, remember this one. So HCl will be the byproduct. Okay, similarly if you let's say if you have this propane, so propane, and you take similarly chlorine, and you take just suppose 1 to 1, okay, one equivalent H chlorine, and you take light. So you have two different types of hydrogens, okay, one CH3, these two are equivalent, okay, and this one is these two, so two sets of hydrogen. So you have a probability of forming uh, two different products. So one will be a Cl, and that the secondary hydrogen will be replaced, and another, in another case, primary hydrogen will be replaced. Okay, so two different products will form. So here, um, you should know that the secondary, this reaction takes place via free radical mechanism. And like free radical mechanism, free radicals are stable with, so when we talk about the free radicals, they are stable, mm, like say methyl free radical. Okay, then you take suppose ethyl free radical, and then let's take propyl free radical, and then say butyl free radical. Okay, terbutyl. So here you see methyl. So here is the methyl carbon, primary carbon, secondary carbon, tertiary carbon. And remember, like carbocations, we discussed free radicals are stable via hyperconjugation. Hyperconjugation. Okay. Hyperconjugation. So you see here, there is no chance of hyperconjugation. Here methyl can hyperconjugate with the free radical. Here two methyls, here three methyls. So this one will be the least stable, then comes this one, then comes this one. So tertiary butyl will be the most stable. So here is the rule. More substitution means higher the stability of the free radical. Okay. So that's why here, although this one will react readily, but we cannot tell exactly the percentage. Why? Because we have here two secondary hydrogens. Okay, here two secondary hydrogens, but six primary hydrogens. So once if we know the percentage of the product, we can calculate the reactivity of the product formation. So this is very important. You should try to understand that how we can calculate the reactivity. So I will give you guys one example. Okay, so the so how we can calculate. So this is the calculation. So for example, if you take is isobutane, okay, and you take one equivalent of chlorine, and in the presence of light, so you have two sets of hydrogens. So one 9 is the primary hydrogen and one is tertiary hydrogen. So you have a chance of making two different halogens. So here you will have the Cl, and plus you'll have CH3, CH3, hydrogen, and CH2, Cl. Okay. So it has been found that it forms 335 is to 65. Okay, so 65% is 1 chloro 2 methyl, 1 chloro 2 methyl propane, and is 35 is 2 chloro 2 methyl propane. So now we can calculate easily. Here is that you have 9 hydrogens. So 9 hydrogens means so 9 hydrogens, 65 divided by 9 will be how much? 7 point something. Okay, let's say 7.2 almost. Okay, and here you have 35, only one, so it will be 35%. So one, so here one hydrogen percentage will be 7.2 almost, and then here you have that only one tertiary hydrogen, that is 35%. So if then if you will take the here, let's say primary, here I'll write primary, here it is a tertiary. Okay, so this one, let's write it this way, H1 and H3. Okay, primary versus tertiary. So what is the ratio? H3 by H1 will be 35 divided by 7.2. So it will be almost 4 point, let's say, so it is almost, you can say 5. Okay, the ratio is 5. So it means that this tertiary hydrogen is almost 5 times more reactive than the primary hydrogen for chlorination via free radical mechanism. Okay, then comes let's another about the synthesis of from alcohol. Okay, that is the free radical, and now synthesis from alcohol. So before moving to synthesis from alcohol, let's talk about uh, using another method. Okay, so if you have allyl or benzyl like hydrogens in a compound. Okay, this is here allyl means this is the carbons, vinyl. Adjacent is the allyl, this one and this one. Okay, so here you have 4 allylic hydrogens. So I'm writing just only one side. If you take this one reagent, okay, um, called halosuccinimide. Okay? Halosuccinimide. And you take, here I'm writing a specific example, bromosuccinimide. So one of the allylic hydrogen will be replaced by bromine. Okay, and your byproduct will be succinimide. So this, so what is the mechanism? So what happens first? I'll write a very brief mechanism. Okay, so if you understand this one, you can write. So succinimide, if you expose to light or heat, so the nitrogen bromine bond breaks homolytically. So this one will make free radical. Okay, so this is an initiation step. So this free radical will take, so the bromine free radical will take the allylic, you can show with any free radical. Okay, succinimide free radical as well, it doesn't matter. So the point is that you will make. So here you will make another free radical. So this one of the hydrogens will be removed. Sorry, this pen is. Okay, we'll start again. So if you take cyclohexene and N-bromosuccinimide, then one of the hydrogens will be replaced by bromine. So the mechanism is first the free radical formation of succinimide. Okay, so this second step will be the abstracting of the hydrogen to make an allylic free radical. Okay, and why this forms? Because this allylic free radical can be resonance stabilized. This is the key. Okay, allylic free radical forms a resonating structure. Now this can react with another N-bromosuccinimide to form the product. Okay, so this is the example. Similarly, if you take benzylic, let's say toluene, okay, here CH3. So, and you take N-chlorosuccinimide, then it will form benzyl chloride under similar condition of the presence of light energy. Okay, why? Because the intermediate here, benzylic free radical, will be stabilized by the ring. Sorry, here the fish hook arrow. Okay, and you can write many resonating structures, and you should practice for that. It will make a resonance here. This can go further here. Okay, and just it can keep on going to make 4 resonating structures. Similarly, iodine can react. So here we found that you can add, okay, the free radical. So you can add that if you have methyl free radical is less stable than secondary free radical, and sorry, primary free radical, and primary free radical is less stable than a secondary free radical, and secondary free radical is less stable than a tertiary free radical, and tertiary is less stable than another tertiary with allylic hydrogen or benzylic hydrogen, a benzylic double bond. Okay, they are the most stable. Before the methyl free radical, even we can add vinylic free radical. Okay, why vinylic free radical? Because vinylic free radical, here you have the highest it is highest S character in this carbon. So on the carbon, you have anything is very unstable, like positive charge or free radical, both they are the least stable. So this you should keep in mind that vinylic free radical means the carbon on the double bond having radical is the least stable, and allylic or benzylic, they are the most stable free radicals. Okay, another important thing is the synthesis from alcohol. So the mechanism for this we will discuss in some mechanisms we already. So like if you have a tertiary alcohol, remember here, tertiary alcohol, alcohol, and you take an acid and anhydrous condition, okay? Anhydrous, there should not be water, okay? So what will happen, tertiary alcohols will be converted into an halide, okay? So this reaction happens via carbocation intermediate. So tertiary are the most stable. So there it will form, carbocation will form easily. So this reaction is not good for primary or secondary. Why? Because the carbocation is not stable. So forming the intermediate is difficult. So the product formation is difficult. For similar, so in that case, if you have like secondary here, OH, okay, so easily chlorinated by using a reagent called sulfonyl chloride. Remember, sulfonyl chloride and a base, pyridine. We'll talk the mechanism in the next chapter, okay? So pyridine base and sulfonyl chloride, SOCl2, it will make Cl, okay? If you want to make of this bromide, so the reagent, remember, PbR3, okay? PbR3 under the similar conditions of PbR3 will convert this to Br. So these two reactions should remember. So alkyl halides, so alkyl halides are important because they are used uh, to make Grignard reagent, one of the important applications. So Grignard reagent, so when you put magnesium, it will, it can be easy to remember here, will be inserted between the halogen and carbon bond. So before that, Grignard reagent and alkyl lithium, we will see the reaction. So if you take an alkyl halide, okay, here I will take bromide, this one, allyl bromide, and you take magnesium. So magnesium can give 2 electrons, okay? Remember, magnesium can give 2 electrons to this carbon, and this carbon will leave with the bond. Okay, so 2 electrons are coming. Here you see this bond pair is leaving. So one electron will neutralize. See more specifically, okay, here I am writing. So try to understand. Suppose bromine leaves, so you will have a positive charge and bromine will have a negative charge. So 2 electrons are coming from magnesium, okay? So one electron will neutralize the positive charge, another electron will give this carbon negative charge. So what will you have a product here? This one negative charge and magnesium, here it will have 2 positive charge and bromine is negative charge. So this is the complete way of writing. Okay, so magnesium, two positive charges and those two negative charges, you can say counter ion. So here these bonds, they have significant, you can say, covalent character. So that's why we write like this as well. Okay, this way we can write, or sometimes you see this negative charge and mgbr. So all everything you can see is same. Okay, here the positive, one positive on magnesium, so different ways of writing. So in all the cases, one thing remember very important is that here this carbon, this, okay, this you have a carbon, either you show a anion, all anions, or you show a carbon magnesium bond, or again you show it an anion and cation. So in all these cases, this carbon is negative charge, means it's a nucleophile, nucleophile or basic in nature. That is the key. Okay, so as soon as it will find an electrophile, it will react very quickly. Okay, so let's say the example, if you have water, okay, so this can quickly react with water and it will be gone as propene and make this will have like this product. Okay, this hydrogen, one hydrogen came from water. I'll give you another some examples. Let's say so if you have like this one here, Cl, benzyl chloride, you put magnesium, so you will get magnesium chloride. Okay, here. So now if you take water, so what will happen? Instead of water, let's just to distinguish, if you have deuterated water, deuterium oxide, okay, D2O. So what will happen? This carbon is nucleophilic as we discussed. So it will quickly take deuterium and what it will form? It will form deuterium attached toluene. So not only water, if you take suppose acetic acid, okay, you take acetic acid. So here see H delta positive, oxygen delta negative. This one is a nucleophile negative. This will quickly react. Okay, and you will get the same product, hydrogen. Okay, similarly, if you take suppose methanol, okay, and in case of methanol, the same reaction will happen. So because oxygen is polarized, active, so this will be the product. So here the point is that Grignard reagents are very active. They will react with reagents that have active hydrogen. Okay, when we say active hydrogen, hydrogen that is more reactive than the alkane itself. Okay, that's why when we make a reagent, we use ether solvent for Grignard, because ethers generally, let's say like this is cyclic ether, tetrahydrofuran or diethyl ether, they don't have OH or active hydrogen. So that's why they are used as a solvent, THF or ethyl ether. Similarly, when you react with lithium alkyl halides, they can lithium can also react. So let us say this, if you have CH3 Cl and is lithium, so it will form CH3 lithium plus lithium chloride. So to write a balance equation, you need two atoms of lithium, because lithium has only one valency, it can transfer only one reagent. So same as Grignard reagents, here methyl has a negative charge and lithium you can say as positive charge. So this methyl is a nucleophile or base. So same, all the reactions will happen like Grignard reagent. It has some different applications as well. So one of the important applications of alkyl lithiums are that they are used to make another reagent called Gilman's reagent. So Gilman's reagent, when two equivalent of is reacted with okay, sorry, copper iodide. So this copper iodide, then it will form CH3 twice CuLi. Okay, here lithium positive and copper negative. So this is called lithium dimethyl cuprate. Cuprate. Why is a cuprate? Because it has copper has a negative charge. So here this one acts as a nucleophile. Remember these reagents: copper nucleophile, lithium dimethyl cuprate. So when this cuprate is Gilman's reagent is reacted with another, mostly iodides. Okay, here is the vinyl iodide. So this vinyl iodide, so what happens? This cuprate is exchanged with iodine. So whatever vinyl, it will attach with copper, and you have two methyl groups on copper. So the byproduct will be lithium iodide. So now here, don't worry about the mechanism. So what happens? This group is exchanged, okay? So the methyl is transferred on the vinyl. So this product forms, okay? Suppose if it is, let's say, just or propyl iodide, okay? So this will form, what will be the product? Here copper, B12 will be, propyl will be attached, you have two methyl groups and plus lithium iodide, and so here see this one methyl will be transferred, so from the propane it will be butane. Okay, so this is all about that alkyl lithium and Gilman's reagent, very basic reactions. More reactions we'll see in organic too. Okay, now oxidation. Okay, oxidation reduction, very briefly. Oxidation means adding electronegative element, and reduction means addition of electropositive element. Now suppose ethane, if you have ethane, okay, you replace one hydrogen by halogens, okay, by chlorine, so it's oxidation. Adding more chlorine is more oxidation. It means this one has a higher oxidation level than this one. and this one has higher oxidation level than this one, than ethane. Okay. Similarly, if you add suppose a nitrogen, okay, so carbon, you have CH3 and carbon triple bond nitrogen. So nitrogen is electronegative element, it has higher oxidation. Or just remove the add oxygen, it will increase the oxidation level. Two oxygens, it will further increase the oxidation level. Okay, you replaced all the hydrogens with oxygen, it will increase the oxidation level as well. So that's how means adding electronegative elements means oxidation. If you have a double bond, okay, and you add like chlorine or bromine, so two chlorines will be attached. So what is this one? Oxidation. If you add hydrogen, okay, hydrogenation, so three hydrogens, so this will be reduction. Now if you add suppose HCl, okay, so what will happen? One H will be added, another Cl will be added. So chlorine is electronegative element and hydrogen is electropositive elements. Both electropositive and electronegative when added. So this one neither oxidation nor reduction. Okay, no oxidation or reduction. Okay, this is all about this chapter. We will do problems in the class, so that in the next class, so that will be that will clear all your questions. Thanks.